I'm going to talk about a multi-model image data set. And basically, we know there are two main approaches for scientific reasoning, deduction and induction. So deduction is really goes from top down. So you have a rule-based system, and we heard in the first session from Kurt, and we have symbolic system, expert system. And when I was a graduate student, and the fifth generation computer research was very hard. And now we have the machine learning data-driven method. So the main approach of artificial intelligence nowadays is inductive. So that goes from data set. So data set is of paramount importance. And we already see many medical image data sets available. And here are just a few examples. And we have the ADNI, so for Alzheimer's disease neuroimaging initiative. And we know this is a longitudinal study. And the second example is BRITS, and this is for multimodal brain tumor segmentation challenges. And this year, the data set has been improved with more images and human labeled results. And also we have the cancer imaging archive, and basically cancer images and with MRI images and T1, T2 proton-weighted MRA and diffusion weighted along 15 directions. And chest X-ray 8 is a NIH clinical center provided data set, and very useful. And very recently we see Mura from Stanford AI Group, and this is intended for machine learning to improve diagnostic performance. And in June this year, and we edited a special issue for IEEE transactions medical imaging under the theme and machine learning for image reconstruction. And here we see a little different. And most image analysis applications really talk about image analysis. So you extract features from images. So go from images to features. On the other hand, tomographic reconstruction is an inverse process. So you start with tomographic data, like case-based data or line integrals. So those indirectly measured data are features. Here we want to go from features to images. So we talk about tomographic image formation. And the medical big data, a lot of kinds. So we focus on focus on tomographic reconstruction. So in this special issue, we included 20 high-quality papers, and the data set were used for MRI, CT, ultrasound, and other modalities. And in this special issue, we see multiple kinds of data set. And the data set were generated basically from real scans, MRI, CT scans, or numerical simulation, and emulation, and we will talk a little bit about this data set. The first well-known data set simulated brain database and from imaging center in Canada. So this is really based on first principle, and according to Bloch's equation, you can generate an MRI data set as you wish. And as we see here, so you have T1 in the top row and the T2 image in the bottom. And from left to right, you see ideal image and the typical one with large noise, large intensity, non-uniformity, and a very thick slice thickness. So all these things you can generate as many as you want. And the second one, MRI, IXI information extraction from images, and from 3 hospitals and groups in UK. So you have kinds of images shown here. And now we talk about CT data set. An example in our paper, and we utilized the CT data set established by Mayo Clinic. This is very useful, and we collected from the Mayo Clinic data set about 6,000 1 millimeter thickness full dose CT images from 10 patients, and also quarter dose counterpart were simulated by artificial noise insertion, and we received pretty good results, and we showed the reference images and learning-based, neural network-based reconstructions. A lot of details in the paper. And on the other hand, we can also rely on numerical simulation more. And last year in fully 3D meeting, and our group suggested approach. So we really do zero energy CT scan of individual patient. Then we deform the zero energy CT scan onto visible human project. So this way we can really colorize the visible human. And also we can use deformable atlas techniques, and we introduce realistic deformations, so we can generate big data set that way. That will be more cost effective, and also label can be brought over. And pathological features could be introduced in numerical simulation. And furthermore, we have a universal CT benchtop donated by GE Global Research Center to our laboratory. And this is industrial platform, and with source detector phantom stages and 9 degrees of freedom, so we can emulate any scanning geometry. For example, when we deal with photon counting technology, we could generate physically realistic data set on the platform. So there are multiple possibilities, and we see the new opportunity. We generate data not only from simulation and emulation, we could combine both. So this is a collaboration with UT Southwestern and Xu in the room, and also with Stony Brook University and the clouds. So we are working on machine learning method to generate big data. So we involve adversarial and transfer learning. This will be a new way. So big data needs could be addressed with machine learning neural network approach. So we are just on the learning curve, hope to produce good results in the near future. And then not only that, we say multi-model data set. And the multiple model data set could be obtained on hybrid scanner. And also we could use deep registration to fuse relevant imaging modality data set. So this slide was kindly offered by my colleague Ping-Kun Yan, and I think also in the room. And he used about 700 data set paired prostate MRI and chest ultrasound images. So they use machine learning to do good registration, and was able, the results show that they could reduce the registration error from 16 millimeter to about 4 millimeter. So this will give us a fused data set as shown here. So this is summary slides. So basically, we say for data-driven machine learning, more data sets are in need, and the public data set already available, as I mentioned, for tomographic reconstruction, and several typical data sets were just summarized. And for data generation, and I would like to underline, and we can obtain big data not only through simulation, emulation, and real scans, but also machine learning, transfer learning, adversary learning will play a big role. And not only individual data set and a multi-model data set, and could be obtained on hybrid scanner and through deep registration for unified analysis and radiomics. Thank you very much.
Jim. So I have a question for Keith. There he is, sorry.
Do we need DICOM headers for tranches of data to define everything on your last slide? You know, the clothes we wear say 65% polyester, 25% wool, and so forth. And yet when we have tranches of data, we don't specify what's in the box. We don't say this is 65% GE generated with a slice thickness of this and a noise index of that, or it's from a 85% Asian American population that's in the age range of so much. But I just worry that we just don't define, we have no way of defining what's in our tranches of data, and to your point.
Awesome question. The ACR DSI is actually leading with the DICOM standards group, the new metadata that we should be tagging, and arguing about whether or not it truly needs to be new standards or if we can expand upon what we have. But we already have the industry as well as a lot of the academics working together right now to try and drive forward how do we expand the tags in DICOM to ensure that we have this type of information. Like even the model version, as well as if we're going to start doing inferencing and dropping that back into the DICOM. So that type of metadata we want, as well as, like you said, give me some non-retraceable attributes of my population so that I know what my model looks like. So we're working on it. Go, Ellie.
Thanks. Well, I'm really happy to see folks from the National Library of Medicine here, because the folks from the National Library of Medicine have done such a great job with tagging and allowing us to search and find a variety of publications. It would be great to see the National Library of Medicine tackle the whole idea of being able to find ways to label data sets. It would be great to have an index and repository, sort of the equivalent of PubMed for publications, for these types of data sets. And it wouldn't only include the DICOM data, but it could include a variety of other types of data that one might use to categorize publications also. So I'd love the question and would very much, there's lots of data that are out there. Lots of us are looking for those sources of data. There are commercial folks who are looking at selling data, buying data, et cetera. And mechanisms to be able to discover that and index that would be really tremendous.
David.
Hi, David Larson from Stanford. Thank you very much for a really provocative discussion. One concept that I really liked was the concept of treating data as something you donate like blood rather than you profit from like currency. And that sounds great, but the reality is, a lot of the institutions or entities that are involved in this are, they're for-profit entities and they're beholden to stakeholders and that have a commercial interest. So how do we reconcile that? How do we, especially when we're hearing from a for-profit company who's the one who's saying, yes, we would love for you to donate. Now, please donate to us that we'll profit off of. So how do we maintain this in a way? But that's to be expected. Like that's what they're there to do. But how do we do it in a way that's fair?
I think you're going to see that funding is going to become dependent upon willingness to contribute anonymized data, if you will, to multi-collaborative trials, multi-site collaborative trials. The institutions will be motivated when clinical trials come down the road where you have to contribute data in order to be funded.
Maybe just one brief addition to that. We have a very nice model in the software community of open source, and then we all harvest it. And we use that inside our equipment. So GE uses a lot of open source software. And it has the benefit of many eyes and the transparency that we talked about. So we know of security, and we know how to maintain said open data or open software. So I think there are other models that we can look at, be it Apache licensing of data, or other open source type models that aren't simply copyright models like we have today or for research only. But I'm with you. I guarantee you're correct. GE is not going to give up all of the data that it's amassed to its competitors without some other larger community effort that comes forward, if that makes sense. So you're spot on.
I think the other thing that's important in the software analogy is the idea of identification with regards to that software. And a lot of these licenses, have verbiage that say if you use this software, you're using it at your own risk. And I think that that's one of the stumbling blocks when it comes to the application of data sets that were created because of unintentional bias and or potential privacy-related concerns, that whether when you have these really large data sets, are they truly de-identified in appropriate manner? So I'd like to see some, HIPAA 2.0 or some sort of addressing the patient privacy concerns that really break down the barriers to large data sharing.
This is Ji Wang from RPI, and I really think numerical simulation could help address the issue. And recently I read some article ranking so-called GAN, Generative Adversary Network, as the #1 hot technology in machine learning field. And I also read conditional GAN could help generate very realistic daily life images. So I hope with machine learning and the medical images could be generated, simulated through machine learning, and that will avoid many privacy issues.
This gentleman.
Yeah, hi. I just want to make a comment about deep neural networks and convolutional neural networks. My name is Bijan Tadayan. My company is Z Advanced Computing. We are a small startup. And basically, all of these deep neural network, convolutional neural network, or reinforcement learning, they're basically statistical. So, in my opinion, they cannot make any reasoning or figure out the conflicts and those kind of things. So it cannot make any thinking. So I call it a specific AI or dumb AI because it's just a dumb box. So you don't know what's going on the box. So for the last 7 years, mostly self-funding and some small funding from other places, my team and Professor Zadeh, who was the late Professor Zadeh, who was the father of fuzzy logic, we worked on an algorithm that overcomes all of the deep neural network and neural network problem. So many layers for cognition and reasoning and things like that neural network cannot do at all. So we came up with some algorithm. Finally, a couple of months ago, we had some demo, and based on that, we proved that you don't need a neural network or deep neural network to do this kind of thing. And basically, we use algorithm based on the general AI. And so what we do is we don't need that many training samples. It's a continuous learning, and you can find features and with some of the one-offs that only maybe a couple of samples out of million exist. So you can learn those like humans. So you can describe things with an nth degree. So it's very different from deep neural network, and it doesn't have any of these things. And even Professor Hinton last year said that the deep neural network cannot generalize very well for data, so you have to throw it all away and start from scratch. So that was a couple of interviews he had before. So basically, I think most companies like IBM and Intel also said similar things, on the use of neural network. So neural network has some usage on a specific AI, but it cannot be useful for all purposes, and it has a ceiling that already reached.
So let me make some comments. And I agree with several speakers. And right now, the machine learning or deep learning is a new area, and a lot of research opportunities, as outlined already. Talking about fuzzy logic system, and actually some work going on in my group. And we basically reproduce conventional neuron with what we call quadratic neuron. So the current neuron, you first do inner product. We think that's a linear operation. So we replace that with a quadratic function. So then you still subject the summary number with nonlinear activation. So this quadratic neuron happen to be a fuzzy logical operator. So if we build a deep neural network with quadratic neurons, then we immediately have a deep fuzzy logic system that offers engineering interpretation of neural network. We hope that will open a door and also a linkage to fuzzy logic system theory and technology. So that way we think fuzzy logic and neural network, they could be combined, synergized together.
Thank you for your comments, sir. Dr. Dreyer.
Thank you, Dr. Flanders. In looking at this field and watching it just a little behind other areas like automotive, I see, in talking to Jensen Wang at NVIDIA, when they kind of went heavily into this space, they realized that the data is kind of the source code, because as you had humans before creating source code, and that was the ground truth of what you have to version, now we're all the way back to data. And so my question is, in your experiences and as you see going forward, whether you borrow the data, you combine the data, or you have weak access to data that's getting smarter annotations, but as soon as somebody corrects one annotation or the software itself corrects it, that original algorithm that you wrote, it now all the way back to the data has changed. So have you thought about versioning back to the data? And if so, what methods are you using to do that? Or where do you think the field's going to go in that respect?
I think that that would probably be a great question. I'd love to hear what Brad Erickson had to say, because it sounds like they've actually built quite a bit of infrastructure at Mayo with their management system to do that curation process. And I think that doing that curation process in a way that's reproducible, like Git is reproducible or source code management is reproducible across software, I think is what's critically needed and critically important for us to go forward. I don't know that any of us have a solution for that today.
Well, on the commercial side, we do. Yeah. So GE is working on that precisely so that we can version and show provenance of exactly what data, which curators, from which sites, and then be able to version that consistently. And this is why I was talking about the challenges inherent in transfer learning if we don't have persistent access to data, is how do you version that? So absolutely that level of provenance, just like in a data warehouse when you do a financial filing for your 10K, we feel that you need it for your 510K.
The only point that I would make as far as not having it is that, you know, Git has kind of become a de facto standard across the open source community, but you've got other things like Bitbucket and Mercurial. So I don't know that we have good generalizable tools that are available across institutions today. While individual institutions are still developing each of these tools as their own kind of cottage industry. I think we need to take that and elevate it so that we can do this in a reproducible way. And I'm not sure whether our institutions, such as our societies, or who's responsible for doing that and pulling that together is a good question. And
I would add one more thing. You know, there's the tools aspect of this, and then there's the methodology and the best practices. And I think we need to actually think about those and define them as well, because having the tools to do this and to curate the data is important, but to make sure that there's some set of guidelines or best practices that everyone can follow as they get into this space is going to be just as important.
Good point.
Yes, Bill Thor with the American College of Radiology. From a patient-centric standpoint, in looking at the shift of population security concerns, whether it be the GDPR in Europe or what's going on after multiple huge hacks of everybody down to the security organizations in the United States. Are we missing an opportunity with this representation of organizations in the room? Just like we have on our driver's license, I want to be an organ donor, and going back to the concept of being a blood donor, should we be looking at public pressure to have facilities distinguish themselves as saying we're a such and such facility because we contribute to our data to a larger entity to contribute to this healthcare provision? Should we be looking for public support for this effort?
It's interesting that the All of Us Think the Science program, and I'm not intimately part of that other than the reference implementation we did, but I've kind of stood and watched. They've had trouble getting partners to pilot this originally. I think originally they had about 15 or 16 different enterprises with major EHR vendors participating. That dropped down to 8. So you're right that it does need some public engagement, if you will, to try to get the medical enterprises, the EHR vendors to all want to participate in patient engagement with the right security model around that data.
This will have to be the last question.
Okay, yeah, I'm Nick Petrick, I'm from the FDA, and I would just a quick comment. I think it's really important to understand that the data is the whole key here, and the data is where the money is, and I think it's very difficult to make everything into sort of a donor, because the patient owns, in some sense it's their data, and it's financial there's money associated with that, and I think the people that can aggregate that data are going to be the people that are going to try to control it and make money, because they're the ones that can make the algorithms. That was my question. I'll go to that question now. The question I have is, how much are we working towards aggregating across not just imaging, but across all types of data? Because in reality, this is obviously an imaging issue, but it's really a general medical issue. And trying to aggregate not just imaging data or not just genetic data in different databases, but trying to aggregate this all together into a unified model where it's really accessible to try to address medical issues. And I just wonder if you guys could comment on that.
Just the comment about the generalizability across all of medicine. I think that gets down to how difficult it is to do normalization. And that normalization problem is exponential when you increase the domain area. So with the common data element discussion that Tessa had mentioned earlier, there's a lot of work that's going on in the HL7 structured data capture areas and things like that. And it's really, really difficult to identify, like, how much do you slow down progress in order to work on the normalization versus how much do you do normalization in a small area and make it publicly available such that you can join in with those larger pieces as they become available. That part's very difficult to answer.
And Nick, I think your question's a really important one, and that is the metadata associated with the imaging. One of the challenges that we have right now with these AI algorithms is a lot of them work in isolation. And we radiologists know what prior imaging studies have. We can go back to multiple ones. We have access to the patient's problem list. And so in many ways, a lot of these things are somewhat artificial now with the subset. And I think bringing in that additional information is going to be really critically important to the success of what we're doing. And even in some of these databases and archives, I think bringing that information in is critical. That gets back to something related to what Keith had just mentioned also. And that is one of the things that was really exciting for me about machine learning is its dynamic aspect. The fact that every new case potentially, for me as a radiologist and my residents, is a learning opportunity. But the FDA ends up clearing an algorithm in a static place, and then that's kind of shrink wrap. And then as I acquire additional data, it doesn't learn the same way that humans might be able to. And so what would be great would be a mechanism where I could refer back to an original algorithm that was tested, FDA cleared, and then it could have some additional thing to say, hey, but at the University of Maryland, based on your experience, here would be information from our aggregated additional data that you have, and maybe have a mechanism to be able to do both. And I know that's a tricky issue as far as clearance, but that would be super helpful to be able to do that, and it would allow a continuous learning environment, as you suggested, from other types of metadata, too.
Just one other point that I wanted to make. I mean, you made the statement that the patient owns the data. And that, I think, is not a completely generally accepted approach. What I would say is that the patient owns a copy of the data, but it's based on there's heterogeneous state laws about who actually owns and is responsible for maintaining a copy of that data and what can be done with it. So I think that there are some serious ethical questions that we need to answer along the way. That's one of the reasons why I think that the more open you can make the data and less tied to a particular commercial interest, the better off we're going to be, because I think the ethics are just cleaner for open and public data than they are for data that's really kind of held as currency.
From a state and federal statutory perspective, it's the facility that actually owns the data from a legal sense anyway.
Yeah, I'm trying to emphasize, I guess, just that there's
control.
There's control of the data. I think I misspoke a little bit. I was trying to just say there's entities that control the data, whether that's the patient or the institution. And I guess the point is there's a lot of money associated with that. So to say that it's just going to be donated and this is a public health, that would be great. I just don't see that as being very realistic. Companies that are larger, that can have more data, are going to try to control that data in a way that they can take advantage of financially. So that part is difficult to see how to work. But I'm all for making this work in a unified way and everyone donate. If that could work, it would be great. It's just hard to see that coming, I guess.
That's going to have to be the last comment. We're at the bottom of the hour. Great discussion, a lot of enthusiasm, awesome session. So everyone has an hour for lunch. Shirley told me to remind the organizers and the invited speakers to meet with her on the
So now it's time for session D. This is my favorite topic, and about machine learning in the imaging life cycle. And my co-chair, Matthew Langren from Stanford University, he will take notes. Okay, anyway. And I happen to be the first speaker. And the title is Tomographic Reconstruction with Machine Learning. Reconstruction has been my most favorite topic. And we have been working on tomographic reconstruction for quite a while. And in 2016, a perspective article, a perspective on deep imaging. And this article has received over 6,000 full text views, so I still feel very confident on this perspective. And a figure in the perspective article shown here, and this is a big picture on smart precision imaging of medicine. And mostly we know these red arrow things from images to features, image analysis. And in the morning I mentioned tomographic reconstruction through machine learning, and go all the way from raw data to final tomographic images, CT or MRI images. So the green arrows and the red arrows, you can just combine them together to form the whole chain. And now people talk about end-to-end, so from tomographic raw data, you can go all the way to radiomics features. And furthermore, you can consider the possibility using machine learning to collect data and use image-guided therapy like radiation treatment, robotic surgery, and this perspective is rather exciting. And I would like to say a few things about general background. Whenever a new project or new technologies appear, and people may reasonably have some concerns. And in retrospective, when analytic reconstruction first came into play, and people had some doubt, like some mathematicians mentioned, whenever you measure finite number of projections, mathematically we can prove and the reconstruction wouldn't be unique. There are some artifacts, ghosts around, and you couldn't measure in the given set of the data. And later on, we use regularization and band limited and so on. So we overcome the hurdle and you use filtered back projection all the time. And then iterative reconstruction algorithms become popular to address like a slow MRI speed or high radiation dose for CT. And when you perform iterative reconstruction, you use some penalty term. And depending on the penalty term and the weighting coefficient, and it appears that what you got and depends on the penalty term. So it seems some subjective nature. And later on, the field worked on the problem, and you can optimize the parameter and so on. You still get a very good diagnostic quality. And then the compressed sensing became popular. And we know even in principle, and with compressed sensing, there is a small chance that the sparse solution is not the truth. So we show example with compressed sensing, tumor-like structures could be introduced, or some pathological plaques may be incorrectly removed. But the problem doesn't stop compressed sensing applied in practice. As long as you do good work with good algorithm design and validation scheme, and you can produce useful results. Now come to machine learning. We heard a lot about black box nature of machine learning, and we know no Maxwell equation for machine learning yet. And you do a lot of training and parameter adjustment, and how machine learning could reliably deliver diagnostic performance we can trust. That is an issue, but that is not something unsolvable. And we produced some good results and with X-ray CT as a particular modality of our interest. And this is a low-hanging fruit, and with machine learning algorithm and the neural network in particular, and we can map quarter dose CT slides all the way to denoise the result, and in good agreement with full dose counterpart. And the article, our group has 2 articles in IEEE Transaction Medical Imaging Special Issue. So you can see detail about how this machine learning algorithm works. Basically, we use a very cheap, cost-effective filtered back projection as a starting point. Then the machine learning offers smart, nonlinear denoising capability that offers state-of-the-art performance. And next example, and we are working on in collaboration with several collaborators on monochromatic CT reconstruction. So normally you perform dual energy CT scan, then you can do monochromatic image decomposition. And instead of performing dual energy CT using KVP switching or dual source or dual layer detectors, and we tried and neural network, we got some interesting results. Just from a single current integrating data set through machine learning, we can do a nonlinear mapping. So we first do a regular reconstruction. The image contains metal artifacts, and along any X-ray path, and we use machine learning map that particular profile into a monochromatic counterpart. And it turned out the result is pretty good. And sparse data CT is another good example. And we implemented a learned neural network. Learn really means learned expert assessment-based reconstruction network. And we unravel iterative process into 10 states. And each stage you still have a regular iterative formula here. Then in parallel to that arm, you have a neural network arm. And any model mismatch not explained by the regular formulation and will be learned through training. So this is something very adaptive, gave good reconstruction result for field view, but similar ideas could be applied for like interior tomography, for limited angle. So we are trying all different things. And several days ago, we posted an article talking about super resolution CT, and we gave the network a name, Gang Circle. The circle really means constrained by identical residue and circle learning ensemble. So putting together, we can get low resolution image, micro CT images improved through supervised and semi-supervised learning, very close to full resolution, high resolution counterpart. And we see about 100% resolution improvement. And 2 or 1 decade ago, and my group published several papers. We use traditional iterative reconstruction to do super resolution deep learning work. At that time, we claim about 30% resolution improvement. Now with machine learning, we see about 100% gain. So that is very exciting progress. As far as metal artifacts reduction is concerned, Professor Heng Yongyu's group with University of Massachusetts Lowell, and they did machine learning, and their idea is to use multiple copies, different versions of initial metal artifacts correction, and put into neural network, and they can combine benefit of multiple algorithms into the state-of-art metal artifacts reduction improvement as shown in the red box. So you see the shadowing basically removed, the streaking artifacts disappeared in the machine learning algorithm. And furthermore, although the training time is very long, and the Heng Yong's group shows that with machine learning and after training, the reconstruction time is very short, and orders of magnitude improve over the state-of-the-art metal artifacts reduction algorithm and named Admire by Siemens. So this is show the speed advantages. So all these examples give us an idea. With machine learning, we can make improvement over state-of-the-art. So any proven algorithm, like metal artifacts reduction, there are some good algorithms, but the result is still not perfect. Then you take that image as your starting point and put the best result into neural network, you will only get even better results. So we can train a neural network to map imperfect or bad results to a best standard. And if you like, you can call it B2B. So we can always improve state-of-the-art algorithm with machine learning. And furthermore, the machine learning algorithm-based, machine-learning-based image reconstruction can be interpreted in a broader sense. And the concept I suggested, instead of doing radiomics, and I made a new word called radiomics. So we go all the way from raw data. And from raw data, you do any reconstruction, you cannot go back. That means some information already lost in the process. So the reconstruction algorithm serves as a feature extractor. And since it is a channel of feature, and why not we do multiple image reconstruction using complementary algorithms? Then you effectively enhance, broaden the space of feature. Based on broadened space of feature, then you perform image analysis, and you do radiomics for better performance. And the whole process can certainly be unified. So you may or may not involve intermediate reconstructed images explicitly. So the whole process gives better opportunity, and you may interpret this as other information, like genomic information, all put together in big machine learning network. So we are actively pursuing research along this direction in collaboration with Amber Simpson from Memorial Sloan Kettering and Bruno Diemann, GE Global Research Center, my colleague Ping Kun, and Manu with MGH. We think this is a promising direction. So this is a summary. So overall, we believe in principle machine learning can outperform iterative reconstruction or compressed sensing. Why? I already mentioned iterative reconstruction or compressed sensing or analytic reconstruction could be used as a component in the neural network or baseline in the neural network. And the training capability and the big data-driven network will perform and step forward. So you will have better performance. So iterative or compressed sensing-based algorithms eventually will be enhanced or replaced by neural network, and that is very powerful in terms of extensive prior and nonlinear learning mapping capability due to big data. Thank you.
Jim Brink from MGH. G, you've been a master image reconstructor for decades, and I was very intrigued by your bad to best application for machine learning. My question is the bad to best potential so great as to be the next big disruption in CT? I.e., do you think it's big enough to take us back to flat panel CT to really improve chrome beam reconstruction to allow us to really replace the rotating gantry?
Thank you very much, Jim. And I do have high-level excitement and confidence. I think machine learning for tomographic reconstruction is at an early stage. A lot of things can be done. The potential is great. And the further development really depends on partnership with medical schools and CT vendors. And I just feel very excited. And the specific answers really depend on availability of big data, rigorous evaluation, and optimization. Many kinds of neural networks, and a lot of work needs to be done.
Hi, this is Pinkeng Yan from Rensselaer Polytechnic Institute. So my question regarding the bias, so as the speakers mentioned, that it's a fundamental problem. So in medical domain, so many cases we don't have the ground truth. We could have just the gold standard, for example, the doctor's labeling, etc. One step further, as Dr. Wang mentioned, that even the imaging reconstruction process that's optimized for human servers, in that process itself, maybe are the bias there. So yeah, for the labeled data, it's very hard to get. For labeled raw data, it's almost impossible to get. So my question is that for our community, as a community, what we can do to achieve that?
So it sounds like you're asking about more labeled raw data. Is that what you were saying, or were you just saying labeled data in general?
Yeah, in general, the bias, how can we actually deal with that?
In general, data. Yeah. So I mean, that's something that it's certainly been a mission of our center. We feel it's part of the academic point of being in academics is to help the community. And so our goal is to try to do whatever possible to release as much labeled medical imaging data as we can. It's not going to solve all the problems. What we would like to do is encourage others who are working on these kinds of projects to begin the conversation with their privacy offices to consider releasing data. We have a process in place at Stanford. It's not necessarily perfect, but it's one that we plan to use because we do think that it's important to have this data out there. And if more people did that, then you can have better models. And what we found is with the RSNA challenge was a great example of this. The team that won the RSNA challenge for Bone Age, it wasn't Google or Microsoft. It was a couple of grad students in Toronto. And the reason they were able to win it is because we released the data for them to use it. So if we can do that more often, we're going to find brilliant computer scientists from all over the globe who are going to be able to do this kind of work and help us advance our field. So that's what we plan to do.
I agree. I think that there's an important contribution that challenges like this, like we're hosting at RSNA. I happen to chair the machine learning steering committee for RSNA, and one of the goals that we have is to foster machine learning, to advance machine learning through competitions, and this is one way to provide labeled data from many organizations to the community. The next challenge, as Kurt had mentioned previously, is going to be on the pneumonia detection. So keep an eye and a year for it. Next week is when we're going to launch it. So those are very exciting times.
Hi there, Amber Simpson from Memorial Sloan Kettering Cancer Center. So we actually just launched a Mackay challenge this year called the Decathlon Challenge. So it was 10 data sets. The idea was to do a generalized segmentation algorithm. The real goal is to make an ImageNet for CT and MRI though, right? So we're putting that out there. We're going to keep going with that challenge year after year to keep building it out. But I want to say that as an individual investigator, I'm a junior investigator. I sit on all this labeled data. My privacy office will let me share it. That's not a problem. The problem is getting the images, getting the annotations buried in the images in such a way that the community can work with them. So whether you do that through DICOM or NIFTY or all these different things. And, we talked about this morning, that's really different across every institution. There's no uniform way to do that. And I'm just a junior investigator trying to make this happen, right? So I got to build this into my grants. I sit there and I'm like writing TCL scripts to do this stuff. Like there's got to be a better way. And whether that comes from NCI or NIH, I don't know. But, we need some support for that to make these things interoperable so I can get that data out there. I don't really have a question. It was really just I want to give you guys data. I have a lot of it. Please take it. Thanks.
I think Amber mentioned very, very important issues. And I would add to that, when we do tomographic reconstruction, raw data format, particularly for CT raw data format, turn out to be very important. In our field, and the data format are not universally open, and we rely on collaboration with General Electric, very helpful. But for bigger picture, if in the future some mechanism, I don't know, if we can make all the vendors' raw data somehow maybe after certain type of conversion available to the research community, then things like the whole work process from raw data end to end to final diagnosis, and not only individual modality. You mentioned the CT and MRI, multiple modalities. So radiomics somehow like unified radiomics, that would give more information. So this is kind of community needs for data infrastructure. I would agree.
Yeah, I agree, G. And, we haven't opened the can of worms yet of how we're going to de-identify or make sure our privacy office is happy that the raw data is de-identified. It doesn't actually contain any PHI, but we have to convince people that it doesn't, right? So I haven't tackled that issue yet. That's a can of worms for another day. But, these are all things in our world that are just stopping us from moving forward.
Hi, Alp Özcan from Acıbadem University. Very exciting talks. Thank you very much. Starting with the bias issues you mentioned with the chest X-rays, instead of labeling pneumonia, you start labeling hospitals. And carrying on from there with the image construction, despite the fact that the medical imaging devices have good mathematical models to define how the reconstruction is done. I'm a little bit concerned that when you try to put AI in for reconstruction, the training set will be influential on the outcomes. What are your thoughts?
I don't do a lot of the reconstruction work, but I agree that there's a potential for bias in that setting. One of the things we have seen with regards to vendor data is that if you train only on one type of scanner, the model doesn't work so well on another type of scanner. And that's even true across the years. And so once GE comes out with version 6.5, my model that was trained on 6.0 doesn't quite work as well. That's a big problem for us. Clearly, if we're thinking about using some of these in a clinical place and something that we have to have in a conversation with our vendors on a regular basis. In terms of the raw data side, I'm certain that there are going to be issues in terms of the transformation as well. Comments.
I was also a little bit mentioning at a lower level of image construction in terms of physical models, changing the physical models with the training sets. Your point is well taken. It is at a higher level, but image construction is sitting at the bottom of everything that we are doing. So, I'm sorry.
I would add to the discussion. I think machine learning capability has been very impressive. And I read some articles talking about conversion from one modality images to another one, like from MRI to CT, CT to MRI. I think if we gave a more general interpretation, would think the scanner algorithm, even the imaging model algorithm, they can be converted somehow. So with that layer, maybe the vendor difference, model mismatch, so on, could be somehow smoothed out. And this is clearly an open topic for further investigation.
One last thing, you could even take that further and reconstruct the whole brain tissue, for instance, if you want to go that far.
Right, that's possible.
Okay, thank you.
And can I comment? Maybe this doesn't directly address your question, but I think we're hearing over and over, does every model need to be validated and trained on every single machine in every single setting? And if that's the case, then we're going to have a major problem with combinatorial explosion very quickly. And so I think we're going to have to figure out ways around that. I think one way that you can look at actually the bone age approach is provided a nice example where the Gorilla Compile standard is a nice standard that's out there, even though it was originally developed on a small subset of Caucasian males. It provides a standard that you can train a model for the Gorilla Compile standard, and then you can then take local variation and connect it or change the weights relative to the standard. So you might have some intermediary, but either way, we're going to have to find a way that we can overcome this combinatorial problem.
Yeah, hi, Ron Summers from the NIH Clinical Center. I have a comment and a question about challenges and their utility in advancing science in our field. In the ImageNet large-scale visual recognition challenge, I think we learned something when deep learning came along and the error rate dropped. could the panel please comment on what we've learned from radiology-focused imaging challenges?
I think that, at least from our experience with the challenges at RSNA, at this point they have been focused on very specific clinical scenarios that the early presentation from Keith this morning showing that grid of all the clinical situations possible, and that it's only a drop in that ocean of possibilities. But we have been advancing the field forward in terms of understanding that variety, the data complexity, understanding the privacy concerns, understanding several pieces related to algorithm development and validation. This is a new field for everybody. I mean, unless you are one of those early creators of the deep learning, you are in the boat with as everybody else, which is we're all trying to figure out as we go. And I think that by exposing these data sets to a variety of different domains and people with different backgrounds, we are seeing a multiplication of solutions in a fashion that very difficult to replicate with the standard publications. And in the previous challenge, for example, the 2017, the Bone Age Challenge, the algorithms, the solutions presented, the top 10, I think they bit the previous state of the art, for example, for that specific clinical scenario. Again, it's one single drop in this ocean, but at least but there are some non-tangible things that are being learned with those challenges that are also very helpful.
One other thing that I guess I would mention is that there's probably been a greater level of humility among physicians. I think radiology, we've always had our mistakes pointed out to us. Somebody says that we take pictures of every one of our mistakes. But I also work with pathology and cardiology, and I think they were probably not as aware of the variability that's starting to become more aware as we build out these challenges and build these data sets. I think that they were much more insular than we were in radiology, and I don't think they were aware of how much variability there was. I think that's probably one of the bigger benefits of this whole challenge mentality in building large data sets is the art of medicine that sometimes got in the way of science medicine.
Could I comment from the perspective of the group who donated the images and speaking of humility, we'd already put together our own algorithm and we knew we were going to get beat and we did quite soundly, but that's okay. And it actually provided a nice, we talked about what's the incentive for organizations to share their data. Well, I think that this provides, number one, it provides a notoriety and the higher profile, but it also really sets the tone, I think, for the whole field. For how we should approach image sharing. So I think that especially given how the level of engagement and just the overall culture, as difficult to quantify as that is, I think it's really critical, especially at the outset of this whole thing.
Could I just add something to that?
Yes, go ahead.
As one of the people who's been participating on the chest X-ray challenge, I'd say that we have actually learned a lot on the committee about what does it take to try to create a very large-scale data set, and how do you do that well? And I think that knowledge is something that you've also worked in, and we're planning on sharing that with the larger community because we're trying to take people who are used to clinical research and really help them understand what's that gap between clinical research and good data sets that work for machine learning. I had another question too, but
you're standing first.
Okay. So my other question is, can you tell us at all what we've heard a ton about image data, and we've also heard that weak labels on a large number of images could be very beneficial for training deep learning algorithms. Can you tell us at all if you're aware of any efforts to create large-scale text data sets that are related to radiology studies, and when we might see those, because the NLP things are so important?
Yeah, you've read my mind. That's another thing on my to-do list, is trying to get our privacy office to agree to allow us to release free text reports, right? Because we really want to have those as part of the data set. Those are better labels than our relatively noisy prospective structured labels that we've released as part of one of our challenges that we've done recently for the X-ray challenge, bone X-ray. But it's harder because, a tiny little slip up and you're in trouble with HIPAA, right? And so we're working on a deal right now. I don't know if this will work for your institutions, but we seem to be close to an agreement that double manual review, meaning having a human trained in city training, knowing all the requirements of HIPAA, with visual eyes on that report twice. And so however fast you can scale that, with whatever budget you're working with, that's how you're getting, at least that's how we've been approaching it. At least that's what it seems like it may require. Whereas maybe Ron could tell us how he was able to release at least the chest X-rays from his side. But for our side, it requires manual review. There's just no other way around it. Yeah.
I'll just comment. We also looked double read every image before we released them.
Hi, my name is Joe. So considering the sorts of noise and data that are in the images that can't be seen, like some of the images that were put up earlier that had a lot of stuff that's not visible to the human eye, do you think that there's room for a new type of imaging that relies only on AI rather than human eyes once we trust AI enough?
I'm not ready to go to a new type. But I do think there are new ways to optimize it. I think a new type could be viewed really broadly, right? I'll hold a flashlight up to you, and that's my new type. But in terms of, MR is remarkably flexible in how it acquires. And, you think about the MR fingerprinting technology where you can, that sort of a acquisition may have a lot more information than what a human can process or appreciate. I think it's very likely that will occur.
Thank you.
I would say that I think the human brain is an excellent deep neural network model, and if you can create it in a way that's visual and we can learn from it, I think that at least I think we've found so far that it's hard to beat that.
So regarding the reconstruction and the bias, the task when we do the reconstruction is always a balance between the bias and the variance. And the regularization we do in all of the iterative reconstructions try to figure out how much to regularize for variance without increasing the bias. I like the approach, which is what we're also doing, a lot of people are doing, of building on top of the regularization from the iterative methods for AI. But there's a word of warning for having AI from sinogram space directly into reconstruction. And the reason for that is there's a lot of physical properties you're modeling in the image propagation that are inherent to every system. That is why there's hope if you had an iterative approach and then on top of it AI to be kind of system blind for manufacturers. I don't see how that would work if you're going to start from the sinogram and then predict from a CT and MR, because that although you're right, there have been papers that showed that, maybe on average that's correct, but then every time there's deviations that are normal deviations, you're not going to pick them up because that was never in your data. Could you comment on that?
I would agree. And how to optimize imaging performance from raw data all the way to the end is not a trivial issue. So really should be done, I think, in task-specific fashion. And we need big data. Since we are talking about data-driven pros, we need the data set large enough, representative, sufficiently many variabilities. So this is something I believe can be done, but it just cannot be generally claimed. And if you have a big data set covering most variabilities, the result should be okay. And the final clinical purpose should be taken into account.
Actually, I'll ask a question for Paras. Putting these things into practice can be a challenge. So you mentioned, like we can have automated And one of the challenges I see is that you have to figure out, well, this is a CTA with contrast, send that to the PE. So how have you thought about making sure that the right subset of an examination or the right exam goes?
Right, that's an excellent question. So I think I was just thinking more high level, but how to do it is really the challenge, right? You know, you can do it by looking at metadata if you have metadata or if you have exam codes. Like at our institution, we actually have very granular exam codes for a lot of these things, and that's one way to accomplish it. But maybe a more robust method that can work across multiple sites is first developing what Dr. Erickson had suggested is maybe CNN to detect if there's a contrast-enhanced study. And if there is a contrast-enhanced study, is it optimally timed for evaluating PE? So there's so many things that need to be developed just to even get to that workflow. But maybe to simplify things, and you know, if you have an informaticist or you have informaticists that can work with your vendors, you might have to have custom solutions at different hospitals to kind of figure out these things.
I think we have a great discussion, and given the time limitation, we can continue interactions after the panel. Okay, thank you.